All right. We decided that we will give two parts of the talk together. So I will give you about the initial talk about the ideas behind what we have done, and then Robert will come up and explain the engineering challenges and how this will fit into the actual practical procedures. So I'll hand it over to Robert when we are ready. Okay, this is a slightly different style of talk because first we will be discussing something that is very ongoing work and also something Jeff talked about, transferring technology from academia to industry. And I didn't know that Jeff was quoting Mark, but it is also work done by not just Robert and me, but also Mark Harman, who is leading the CREST, where I come from. So it's a research center, University College London. It's called Center for Research for Evolution, Search and Testing because, well, it has evolution, but it's a software engineering lab, really. But the reason why we have evolution in the title is because we are quite passionate about using meta-heuristic search algorithms for engineering problems. So it has wide array of expertise, but we are quite big on testing. So there are people who's doing automatic test data generation, as Jeff mentioned. He actually had search-based technique on the slides. We do mutation testing. I'm working on regression testing, but there are people also doing requirements and also not search-based stuff, so static analysis and other things. It's based in very central part of London, so if you ever find yourself in London and want to talk about these things, you are always welcome. And the center, as I told you, is very big on search-based software engineering. The whole theme is the very obvious fact that optimization and research into trade-offs between different objectives is always very essential to any engineering disciplines, mechanical, civil engineering, and the main idea behind SBSE is, why not software engineering? We are engineering. We are in the engineering discipline, so why can't we use them? So the whole goal of SBSE is to formulate problems in software engineering into optimization problems, and then try to apply various techniques from this rich array of optimization library. There are, literally hundreds of algorithms devised by evolutionary computation people and all sorts of other disciplines. So we just need to pick one and apply it to your problems. So we have seen some very interesting results recently. So there was a paper that surprised quite many people last year, which was one about automated bug patching by Wes Weimer and Stephanie Forrest last year. So what they did was to use genetic programming to build a quick patch for a known bug automatically, and it worked quite well. We had a paper about human competitive results in various areas, so they applied it to regression testing, requirements engineering, and the result that these algorithms gave was also annual international symposium. So now that was the sales pitch. This is the outline of the talk. I'll give you some motivations, and then we will go into define what we call dependency coverage for large systems in shared code repository, and how we optimize the regression testing problem we have and some initial result, and then I will hand it over to Robert for engineering challenges. So I probably do not need to motivate you very much about the problems of regression testing. The definition we use in the academia, regression testing is performed to gain confidence. That's because you cannot predict the fault, but you can only reveal the existence. But you want to essentially gain confidence that the recent changes did not actually damage the existing systems. There are very many techniques developed for this, mainly because as the software evolves, your regression suite keeps growing until it is not feasible to execute all the tests that you have. So there are three main pillars in the literature. Minimization, you try to get rid of redundant test cases. Selection, you want to precisely select those that are relevant to recent changes only. And then finally, the prioritization idea is you want to run what the most important test first. And these are all techniques invented to deal with increasing cost of regression testing. But I say, in the modern development environment, all the tests share some dated assumptions. So first, they all assume that we have a fixed release cycle and fixed shipment date, and you are working towards this next goal. And then it also assumes that the tester, or well, in some cases developers, but all the techniques assumed that the person who's applying these techniques has the ownership of the entire code base. So for example, it assumes that you can get all the instrumentation for coverage, you can inspect the source codes, that kind of things, which may not always be available. So I sense that there is a new trend emerging, and it is mainly for the world of web applications and these small apps that we use more and more frequently in our everyday life. Nowadays, especially in the web application world, software is not released and shipped. They are made available in incremental and continuous way, which means the pressure to time to market is very enormous. And then we often have distributed development environment, and the source code is shared over large repositories. And you may not break your code, but someone else's by making changes. And it's very hard to predict when you're working on your module. When I showed these slides to Robert, he panicked because no one does waterfall model anymore. And as soon as I see one on the slides, I know that I can sleep for the next 5 minutes, but don't worry. So this is the classical model, but I will skip it. And then we had Agile. I'm not so sure you can represent the whole Agile movement by adding one more edge on the graph, but there you go. And I think we are probably moving towards the next generation of paradigms. And what it means is probably that this cycle is getting so short that now everything almost happens concurrently. Robert suggested the term push by green. So you don't have a fixed shipment or release date. You just try to keep everything healthy in your repository, and then when everything is fine, then you push out the next release in an incremental way. So yeah, what we mean by push by green is probably that the iteration time for this cycle is now converging to zero. Everything happens concurrently. So testing should happen while you are developing, and it should help the development itself. So the automation probably plays a central role here, because otherwise it will be too costly. But it's not just about being cost effective, meaning shorter time to test, but any guidance we get from automation should, if possible, allow the tester to measure the trade-off he gets. And by giving the early test feedback with this measurable trade-offs, it will enable the developer to achieve shorter development cycle and decrease the cost to fix regression faults. So what does it mean in concrete terms for the developer? The automated tool should guide your testing by prioritizing, so suggesting some tests that you should run at this precise point. So the goal is to achieve early test feedback and to select a set of tests that will yield the highest chance of breaking something, but without owning all the dependency, because we are working in a large repository, and then to be able to observe this cost-effectiveness trade-off precisely. So what we suggest is a heuristic, and you can see that now I'm coming from meta-heuristic camp. A heuristic that selects tests that can be executed within specific budget. We often talk about cost in terms of time, so it's within specified time for a particular code change. And we will base our decision on testing the dependency relations. So you want to ask, did I break anything that's depending on me? History of fault failures. So we will assume that what has been broken in the past probably has high chance of getting broken again. And then any other information that you care about. And this is one very strong point about using meta-heuristic search, because anything that can be formulated into your objective function for your search algorithm, you can optimize. So these are the things that we'll try to optimize in this small pilot. So first one is the cost. You obviously want to minimize it. So we will depend on a automated testing framework which has all the metadata from the past execution of your test and try to extract the cost of each test you have in your system. The second one is dependency. We will not use the code coverage as a measure of effectiveness of your testing, mainly because you may not know all the code level coverage of the modules that's depending on you. You may know everything about your code, but there are some modules that are owned by other people and they may get broken. So in the literature in regression testing techniques, the most widely used criterion is probably the structural coverage, but it may not always be available, and we want to aim our approach on this large repository model. So instead of code, we will focus on a graph of the dependency model. So what we eventually get is something like this. So this is your module. You are developing on this and you want to test this. And if you are a good developer, then you should probably done a lot of unit testing on this module. So this one and anything else that your module is depending on has been tested. But there are other targets that are depending on your module, and then eventually there are some tests that test these modules and also perhaps your own module. And we have this structure that looks like a cone. That's what we termed. So we will define a new coverage on this graph. So essentially it is the number of things in the cones and number of things your test touches by executing the test. So one added benefit of defining this dependency coverage is not just to detect breakage in the modules that depending on yourself, but it also enables the developer to see outside of the directory that he's working on. So meaning, if you are testing your code, then you will probably care about the code that you have written and everything else you're depending on, but it's very hard to see outside your box and see other modules that are depending on you, but that can have the most dramatic aftermath if something goes well, if I may say. So it makes it possible to touch all the affected pieces of code in order to avoid any danger. And the third objective we considered is history. So we had the support from this large test framework in Google when we did the pilot. So for each test, we could count number of failures in the fixed amount of time before our testing. So obviously this we want to increase, as well as the dependency coverage we talked about. So the assumptions we are making for this optimization: if you get higher dependency coverage, it's better because it gives you a higher chance of detecting a failure in arbitrary location behind you. And by including history, we are expecting that a good test which has detected something before will again probably detect new failures. And then we want to maximize these two within the given CPU time. And the way we do it is by using genetic algorithms in this case. So I won't go into details because it has a whole stash of papers assigned to itself. But essentially what we are doing is a multi-objective optimization. So you get to minimize your cost while trying to maximize whatever goal that you want to maximize. So this is actually a trade-off observed in one of the real modules in Google's repository. So what it's saying is, as execution time grows, you will get more and more dependency coverage. And this trade-off is quite frequently observed in any code, whether it's dependency coverage or statement branch coverage. You get a graph that looks like that, and there is a point where the trade-off happens. So the question you should ask yourself is, this is often the 80-20 rule. So is this enough? Well, we'll see. So that's what we did in this small pilot earlier this year. Actually, I spent May in the Google Zurich office, and we looked at some change lists submitted to the Google's repository. There is a small caveat. The history data we used for this pilot was actually not real history, but some future. But at that point, we didn't know how to dig out the data from the infrastructure, and it was quite difficult. But at the same time, we thought, there is nice continuity in this testing effort in Google, so it will probably work. And Robert will give you more explanation on this later, but we did not filter out the Flaky test. So this is where I will probably spend the most of my time. So this is one of the good results, and you will see, again, this familiar shape. So on the x-axis, we have the CPU time required to execute your test. And on the y-axis, we have the dependency coverage, and it sort of flattens out after you spend a certain amount of time. And there are black dots and red dots. Red ones are the set of tests that detect failure. So if you want to be complete, then you can choose this set, which will require quite a lot of CPU time, but also gives you high coverage. But if you are really short of time, something along this region will still notify you about the breakage that you just made. On the right side, we have the comparison of the CPU times. So the total CPU time is the time required to execute all the tests that are in the cone that we looked at earlier. So this is the time required to execute all the relevant tests for the module that you are submitting. And the middle column is for the required CPU time for the maximum coverage. So essentially, that's what it takes to execute this point. And finally, the left one is minimum time for failure. So it's the CPU time required for executing this point. The problem is you cannot predict where this point will lie always. But between this and this, you can probably get reasonable policy. So for example, you will always cut this graph in half and pick some point closest. And we have some other result that shows similar patterns. This one is quite interesting because you get a lot of those similar patterns, but only one of them are actually red. It is interesting because all these are increasing dependency coverage as we allow them more time, but only the rightmost one actually detects some fault. So what it tells you is the tests in these lines are actually touching the dependency, but probably not doing enough to actually detect the failure. Whereas if you start to spend significant amount of CPU time on this test, you will actually include the test that detects the failure. But this being meta-heuristic and also a testing problem, it's always not so good news. So in this case, we required quite a lot of dependency coverage to get the first failing test. The same here, and even none at all. So this is something that we can improve upon. But as a summary, out of 24, 18 CLs provided good result, meaning that we were able to prioritize and select some subset, and they still detected failures. Average CPU time required to maximum coverage, it's less than 50% of the time required to run everything. Average CPU time to require the first failure, the leftmost red dot, it's about 27%. And to require the first failure, you only need about 70% of the coverage. So it's, again, sort of the 80-20 rules here. So that was the pilot. And ever since, we have been doing this ongoing evaluation. So what we did was we ran a process, and we have been picking random CLs to apply the optimization. It had to be automated, so it actually means that out of those graphs, you have to pick a point to select the tests that you will run. So we decided to be very conservative and allowed the algorithm to have 50% of CPU time required for running all the tests. So overall, we will always get 50% save in CPU time. And this time, we knew a lot more about the infrastructure, and we were able to filter out flaky tests before starting the optimization. So this is the result from the ongoing evaluation. We have a number of tests here. The blue column is what the testing infrastructure in Google considered for the submitted change list. And the red column is what we chose based on the metadata and the optimization. And on average, we are selecting about 66% of the tests that TAP considered. So it's a saving of about 1/3. In terms of effectiveness, about 60% of time, the prioritized test detects breakage, and about 40% of time it doesn't. This is out of 60 change lists randomly chosen, and the real breakage data was again collected from TAP. So this probably doesn't look as good as the pilot, but we should consider 2 points. First, because we are filtering out flaky tests, it's a bit hard to detect a real breakage. But still, it's not that far off from the pilot, and we succeed slightly more than half the times, which is better than the pilot, but the reduction is slightly less. We save about 1/3. But again, what we should remember is we choose a very conservative policy of allowing 50% of CPU time budget, whereas the real failure point, the leftmost red dot we saw on the graphs, may be significantly cheaper than the 50% CPU time budget. And this is where our next work lies. So we need to find a realistic way of finding this threshold that gives you significant saving while being reasonably effective. Okay, so at this point, I'll hand over to Robert, and he will give you some details about the engineering challenges.
Works. Yeah, so one thing to keep in mind here is that one of the targets for this is to be for the developer, and he's in the state of mind of developing his software. He just wants to run the test as a side activity all the time, and he wants early feedback from what he's working on, right? So if you can have this, and then you can have like something in the back of your, running in the background of... Okay, so can you help me? Yeah, so this is targeted somewhat at engineers who are in the flow of developing, and they want to have still the backs free. So they want to find the problems where, they break someone else in the big integration system. So also for doing this and actually using it in action, there is an artificial constraint from an academic perspective. Like, these things are not something that we'll talk about probably in a... Okay. Sorry. Hello. So I wouldn't talk about in an academic conference, but software engineers are very impatient creatures, and if I tell them that, hey, you're going to have to wait 10 or 15 minutes for an optimization to finish, it will save them some testing time. I'll say, okay, why do I need to do that? We have a search engine where I can type in a word and we prioritize all the web pages, and it takes like under a second. So why should I wait 5-10 minutes to have my test prioritized? So I couldn't do that. So we need to do some processing offline to make this like appear to be instant, basically, right? They don't want to run stuff on their desktop because they have other stuff to do on their desktop, and they have this kind of annoyance of flaky tests. And Flaky we'll talk about more later, but this is something that goes around Google a lot, where we have false positives, basically. Something say, oh, something's broken, but really it's not. So you spend time investigating things and losing time and productivity. Another thing that you don't want to run into is to measure your change to the system or the change to whatever you're developing against something that's already broken. I mean, you want to know that your thing that you're introducing or adding to the system is nice and clean. You don't want to be affected by whatever else is going on in the system that's evolving around you. So, yeah, and another thing that I have experienced from other projects is that if you present like information to engineers and developers and you just give them like the facts on the table, they'll be, okay, so how did you do this? I mean, this like, where does this come from? So they want to have some kind of insight and explanation to what kind of suggestions you gives, and be able to understand it at least on some abstract level and have some kind of control saying, okay, this is really stupid, I want to do this instead. If I just say, okay, wait a minute, or wait, actually not a minute, wait half an hour and I'll run all the tests and figure out this for you. This you can take, okay, why does it have to take half an hour? And then I present to them what we are doing and say, okay, but that and that and that is very stupid, so why do you do that anyway? And okay, this is again very unscientific because I tend to do like a survey and this kind of stuff. It's like just things that I've been observing working with developers in my job. So the Flaky test is something that you heard before. I think Simon mentioned this as well. It comes from, it's actually non-determinist of a test result, and it comes from multi-threading, pseudo-randomness in your testing. You can have timeouts from resource overload, like you're starved on whatever CPU you're running on, or there is some resource that you need for your test that you can't access, like test accounts or something like this. So as part of this work, just after Shin left Zurich, we said that, okay, this flakiness is probably going to be a big problem. We don't want to suggest flaky tests to developers because it's going to make this tool more or less useless. So we thought, start looking at how can we kind of come up with a heuristic to determine if a test is flaky or not. To some extent, we could get this from manual annotation. People would know, okay, I'm doing this, I know it's going to be flaky. It's like a big UI test or something. It's going to be very hard to get it right all the time. But there are also a lot of places where people haven't annotated, and there's still a lot of flakiness going on. And we basically looked at awesome test infrastructure we have at Google, and we can just see like the history and see, okay, this is a flaky test, and it has a pattern which looks like this, that we have usually a cut where it goes from passing to failing, because it's very unlikely that the developer will catch up and like fix the problem exactly just off the one change list, or a change in this case, or submit to repository. Whereas a flaky thing looks like more like irregular pattern like this. And we basically extracted heuristic from where we count the number of transitions here with the length of 1 for the failure, like the pass, fail, pass transitions. So while we're developing this, there's actually other people in Mountain View in the headquarters were doing similar work, and it turns out that we could set up meetings and collaborate on this, and now this is actually part of the common infrastructure we have. So this is a metric that is exported. This is really good. So what we want to use test prioritization for here is to like perform analysis, and we want to do it so it appears to be super fast. We do it while developers write their code. And we want to do either just conservatively, so we have a good chance of finding a breaking test for them, or precisely say, okay, I'm going to go to the macro kitchen, I'm going to have a coffee. I have 10 minutes and give me the best shot at finding stuff that breaks so I can go back here and fix them later, and then have a less probability of submitting and finding out like in half an hour or half a day later that, oh, by the way, you broke someone else and got an angry email or something. So if you have this thing, you can run it and you can get early feedback, and then you can just choose to go ahead and submit it, or you can run the rest of them if you are still insecure of if the risk is very high, if you wish, right? So this is not rocket science. It's like just a small tool that has a basic server, but it has like a component where you actually spy on the IDE of the developer. You see what are they doing right now, and this means that we can, start batch processing and figuring out what you need to eventually run to validate this change. And we have some threading going on here, which talks to our backends, which contains all this nice test metadata and stuff that's collected by our continuous integration system. And then when the developers need this, they can just go ahead and they get information as appearing as it's super fast, right? So this is how it looks on my screen, because I'm like, cool, I use black and green. Actually not, I'm just using, this is like how the tool looks like now, this prototype thing we developed based on this. So it's a command line thing. You can see, get a risk estimate here. So you see that, okay, this change you did affect 129 tests and 21 libraries across the package. You get a list of what kind of things that you are modifying, because maybe some of these packages up here are more important. So maybe we might be really sure that I never break the build of the new evil validator, for instance, because then someone will come and beat me with a stick. Whereas I'm not as concerned about this thing or something like that. I think it's very unlikely that I will break this. So this is how it looks like now. This is a very early beta, as I said. What I would like this to look like is something like this. So this is vaporware, it doesn't exist. But you would like to have this breaking down by test type. Okay, what kind of test do we have here? UA automation test, integration test, unit tests, and so on. If we had manual tests in our dependency graph, which I think would be an interesting idea to try out, we could also have like manual testing cost here. Like, okay, if I submit this, we're going to have so many manual tests we have to run, taking so many hours. And then you have the same stuff as before, and instead of having the CPU time, which we have today, we would have estimated wall clock time, saying that actually this is the time you have to wait for this. And also things like, who is the people who cares about this thing? So maybe I want to make sure I never break Gmail because Ankit will come and be angry at me. So then I want to prioritize maybe more these tests. And so the kind of options you want to give to this thing is say, okay, I have this information and I want to guide the prioritization to take into consideration like a spread over these or more integration tests and focusing on Gmail, stuff like this, right? So this is like visionary development here. So this was like for the tool. Then if you look back at what Shin described, actually dependency cone problem and so on, or dependency coverage, there is some fundamental things here that can cause problems that it realized when we were trying this out in practice, that this dependency relation is kind of statically defined in a way, and it can be very weak or very strong, and you don't know. So if you had like structural information about code coverage to enhance this, it would be better, because then you could say like, how strong is this dependency from this model to this other model, and make a better prioritization. So it happens that we sometimes think we have dependencies, which is very incidental, which is very not really a big deal, so to say. And then we also have this related problem where we sometimes see that we have hotspots or landmines in our dependency graph. So this code that I'm changing right now could be pulled in by some of our big binaries, like the search front end or something. And then all of a sudden we have thousands of UI tests or even more to run. Lots and lots of work. And then we have a very hard time to know what is a good thing here, what to run and what to not run. So this is something that we also would like to have a better dependency concept to flesh out and do a better job. So I mentioned in my tool slide that we have some mem caching, or I've showed it on the slide at least. So we have to do some caching over the repositories we have, and also the systems we have some caching internally. So there is some problem with freshness, that the data that we're actually going to use in our optimization is going to be a little bit stale. That would be nicer to have, but we can probably live without it. The CPU time to wall time is very hard to predict if you're running your test and building things in a cluster, because it depends on a lot of caching and parallelization aspects, which is hard to model, and we would need to have like very much better APIs to our build tools to get this information out. Another thing that is related to the previous one is that actually, because we have caching on many levels, as Nathan did an excellent talk on the pre-GTAC talking about this, we have caching on so many levels, it could be that the cost is actually conditional, so that if I build this set of things, the test becomes cheaper, because I already done lots of the work, right? So you can maybe rephrase this cost of the test in terms of what things you've already built and the work you've already done. So it becomes another search problem, trying to find in this space of actual cost, given that you have done work previously. So wrapping up, outcomes of this project that we have done so far. So we have this dependency coverage concept within Google, which is kind of interesting. We have input to Google teams about various metric prioritization and ideas, basically here. We did an open source library because it turns out working with academia in Google is kind of hard. I mean, Shin wouldn't have all the access that I would have, so we actually split it up. So Shin was working on some code in open source library, and I was working on some stuff inside, and we made sure that the interfaces were anonymized and clean and whatever. Another thing which I think is an interesting one is that we have a great understanding about Google kind of problems in academia. So communication with Shin, seeing what kind of repositories we have and what is going on inside Google can help lots of PhDs to focus on this problem maybe and get some more academic results that are useful for us. We have potential benefits which we don't know we might have sometimes in the future. We can give the developers this risk estimation thing, right? In the tool sense that, okay, if I have this information before I submit to the repository, I know what kind of things I can affect. I can choose where I want to spend my testing effort. And in some cases, I can deprioritize manually some parts and not others. You can also have this CPU. If you run this as a pre-submit scenario, you can save CPU hours, basically, by not running all the tests and still getting a decent warning, so to speak, before you run everything in the post-submit case. Yeah, and as I said earlier, feedback is another aspect of this. So what are we doing now? Continuing evaluating this thing on more random change lists or changes into the repository. We would like to try different heuristics and try to be even better, obviously, see if there's some other signals that we can come up with. Maybe one signal we want to try is this obvious one that we have historic data where when editing one kind of change cause a test to fail in the past. That would be like a really good indication that we should run this test again. Right now, we just have an absolute notion of, okay, this test fails a lot, and it's not flaky, so then we probably want to prioritize that in front of another one. Yeah. So also this problem I mentioned, do it better with dependency graph and make this tool more useful, more like the vision I had, basically. Amazing that something that developers actually would like to use and to see what feedback we get from that. And that's about it. Questions? Come up here, Shin.
As we are short of time again, we'll have a couple of questions, and we request everybody to just ask one. In case you have a follow-up, please talk to Shin and Robert in the break. Any questions? Okay, we can have more if you're... Okay.
What does a dependency analysis take into consideration non-code dependencies, such as a module A updates a file which module B then reads, changes the data structure, which is not evident?
In some cases, yes, but not always.
Have you done any retrospective analysis to see what bugs escape?
That's very hard to observe on the current infrastructure because almost all tests are running probably all the time. So even during the time we run the optimization, someone else can actually pick up the test and run it and may pass or fail. So it's hard to isolate what our approach has exactly done. And it's one of the problems, especially for me if I want to present it in academic setting, but we're sort of working on it. And actually, it poses a very challenging set of problems, I think, because essentially we are testing too hard in this case. So you are not always able to observe what your testing has done to the system, but you are always observing someone else's result as well as a sort of continuous stream. So we need to work on this to evaluate this more clearly, I think. The dependency, we actually didn't analyze it out by ourselves, but we sort of picked it up from the dependency relation server that's running in Google's system. So you can query and get some relationship. So you give a file and it will bring you up all the files that are depending on it, and depending on that information.
Does the system learn over time so that if a test proves particularly useful or particularly good at detecting faults, will it get chosen more often? Or is that something you've looked at adding?
Can you repeat that, please?
If a test proves particularly useful at catching bugs, is it more likely to get chosen in the future? Does the system learn over time to evolve and
certainly
become
that's our hope. And in this case, the positive feedback route we have is if a test is particularly good, above average, then it will show up as higher number of past faults detected for that by the test case. So that should be prioritized by maximizing on that objective. So they should have a higher chance of being selected, given that it fits in the budget that we have.
Yeah, and also if you have this more explicit mapping from file to test, then there's going to be even more of a learning factor in there. That this file is actually very good to test with this set of tests or something like this.
Right? Thank you very much.